and this is lecture number 16. In this video, we're going to study about differentiability and continuity of functions. So what is differentiability and what is continuity? Let's look at continuity first. Continuous functions or continuity. And let's look at what is continuity, and then we'll build a theory on differentiability. So we have a theorem. You say a function is continuous at x is equal to a if the limit as x approaches a of f of x is equal to f of a. In other words, f of x must be defined and f of a must be defined. Right, so this is the definition of continuity, but note the limit as x approaches a can be further broken down into limit as x approaches a from the left of f of x, and can be broken down. It must be left and right must be the same. A from the right of f of x. Right, so if you're looking at a number line, to explain this, this is a value a, this is a from the left, and this is a from the right. Now, how do you know which one is from the left? You're approaching from the left and you're approaching from the right. So when you say limit as x approaches a, can be approaching from the left, so this is less than sign, or looking at less than equal to sign. A from the right, if you have a split function, is greater than sign or greater than equal to sign. Okay, so that's basically basic definition of continuity. Now you get various types of continuity, which I'm just going to draw on simple graphs and show you the types of continuity you get. You will see that you get graphs like this, right? Continuous function is a function where it is defined at a particular point. Now, if you're looking at this type of function, it is continuous everywhere except at, I'm going to put a hole in this graph here, and it's undefined at -1, all right? So if I ask you, what's the domain of this function? You say domain is x is an element of real numbers, but x is not equal to -1. Yeah. So in other words, this is discontinuous. So we see it is discontinuous at x is equal to -1. Why it is discontinuous? Because limit as x approaches -1 of f of x, the answer is limit as x approaches -1, that exists, the value is 1, but this here works, right? This is equals to 1. And if you're trying to find f of -1, that is undefined, okay? So you see, the definition of continuity does not work. Limit as x approaches -1, yes, that value is 1, but f of a itself is undefined. So you can see what happens here, it fails. So we say this is discontinuous. F is, this function f is discontinuous at x is equal to -1, and the type of discontinuity is removable. Discontinuity. Are we good? So removable discontinuity is a discontinuity that has a hole in the graph. Number 2, the second type of discontinuity. I'm just doing this in general, right? But you will see more different types of functions. I see that you have some kind of a graph, maybe a quadratic function, okay? It starts at 1, right, and continues upwards. And you have another function down here at -1, and it's linear, right? And this value is -1, and that value is 1, okay? So we want to find, let me try to make this thing a little bit more steeper. So see, this bottom piece is including, this top is excluded. So if I try to find limit as x approaches 1 of f of x, how am I going to find that? I can't really find because I've got a split function. I've got limit from left and limit from right. See, the limit is approaching from the left and the limit is approaching from the right. Not 1, sorry. Limit as x approaches 0. What's the behavior of the limit at 0? So I can't really find limit as x approaches 0, but I can do the left and right, okay? If I approach from the left and approach from the right, I get two different values. So let's see. Limit as x approaches 0 from the left. If I approach 0 from the left, I'm getting a value, y value, which is -1. And limit as x approaches 0 from the right of f of x. If I approach 0 from the right, I'm getting 1. Okay? So the limit does not exist now in this case. So limit as x approaches 0 of f of x, what's happening here? Does not exist. But sometimes f of 0 does exist, and that value is -1. This is defined. F of 0 works, but the limit does not exist. See the previous one? The limit existed, but that was undefined. Over here, this is undefined, does not exist, but this works. So in both cases, we can see that does not exist. Why? The limit as x approaches does not exist because left-hand side limit is clearly equal to, is not equal to. So left-hand side, and you can call it RHS. Left-hand side is LHS, and call this RHS. So why this limit does not exist? Left-hand side is clearly not equal to right-hand side limit. Instead of writing out this whole thing, I'd rather write this down. And you see the type of discontinuity you see here, you say, so you can clearly see over here is that limit as x approaches 0 of f of x is clearly not equal to f of 0 because this does not exist, and so it is, f is discontinuous at x is equal to 0. And what's the type of discontinuity? A jump. We have a jump discontinuity. Right, guys? Making sense?
Yeah, one question,
Excellent.
teacher.
Yeah,
Just a
yeah.
second. About so the jump discontinuity will become when the limit is not exist in the case when it's not approached the line, or what? The line is not going from the 0. How did you say that? I didn't understand.
It's jump discontinuity because you can see there is a jump in the y values. Look at the y values, -1 and 1. So this is a jump discontinuity. As the name suggests, there is a jump in the y values. Do you understand that?
Yeah, okay.
Look at the graph. Look at the graph. There's a jump in the y value. So that's where the jump is. So the jump discontinuity is see -1 and 1. So there's a jump in the y values. is not existent because this is -1 and that value is 1. So there's a big jump. That's creating a jump here. Limit from left and limit from right. It's creating a jump. If it was the same y value, then the limit will exist.
That's why 0 is not exist, yeah? Limit is not
Yes.
exist in that case.
Yes, because what does discontinuity mean? The graph is broken. So you are testing where is the graph broken? What type of broken graph is it? That's what you are testing. Make sense?
Okay. Yeah, makes sense. Yeah.
So that's what you're looking at.
Okay, thank you.
Next one. The third type we get is infinite. Infinite discontinuity usually deals with the asymptotes. It's always discontinuous at the asymptotes. Now, remember we did some rational functions. So I'm just going to sketch that basic rational function y equals 1 over x. Right? So right, and I'm going to check the discontinuity at 0. What's happening at 0? If I approach 0 from the left, and if I approach 0 from the right, what's happening? So when I approach the graph from 0 from the left, is going towards positive infinity, the y values, and 0 from the left is going towards negative infinity. So limit as x approaches 0 from the left, this is left-hand side of f of x is equal to negative infinity. 0 from the left, the graph is going towards negative infinity. Just say this is a function y equals 1 over x. And RHS limit as x approaches 0 from the right of f of x. Why 0? Because that's where the asymptote is, okay? If it was pi by 2, I would put pi by 2, like the tan function. The asymptote is at pi by 2. So 0 from the right is becoming positive infinity. You can clearly see left-hand side is not equal to right-hand side. As long as there's infinities here, doesn't need to be negative infinity, positive infinity. As long as there's infinities here, there will be an infinite discontinuity, okay? So there's an infinite discontinuity at 0. So we can clearly see limit as x approaches 0 of f of x, that does not exist. Why it doesn't exist? Because we're getting two different values. It may exist, sometimes it can become infinity, but f of 0 is undefined. This is the main thing. So this is undefined, and sometimes this can be, it does not exist, or it can be infinite. So we get an infinite discontinuity. So what we say, why is this discontinuous? We're going to say limit as x approaches 0 of f of x is clearly not equal to f of 0. So we say f is discontinuous at x is equal to 0. Why? Because of infinite discontinuity. Okay. And there's one more, which is oscillation. Right, so I just want to go through the notes. Look, we have did the jump discontinuity, a removable infinite discontinuity. I'm just going to look at oscillatory. Right, so when the function is differentiable and domain. So let's look at what is differentiability. I'll have to just do it now. So we did continuity. What is differentiability? Differentiability got to deal with differentiation. So we say a function is differentiable. A function is differentiable at x is equal to a if the differentiability from the left is equal to differentiability from the right. See, f minus at the bottom means left hand side differentiable, right hand side differentiable. Okay. So you can say x, and you can say a here. So you replace the x with a from the left and a from the right. Okay. So let me just replace it with x for now and then change it to a, which implies that's what it implies. Okay. So if you take out, so you're differentiating left-hand side function and the right-hand side function at a. In other words, you're looking at a split function to check for differentiability. See, this is a from the left, and this is a from the right. So in other words, you will be checking for less than sign, greater than sign functions, right? This is a from the left, a from the right. So looking for less than, equal to, greater than, equal to, for the signs, in the split function. Now, we have a very important concept. If f is differentiable, then it is continuous. Very important, right? And I've highlighted this in my notes. This is a very important thing. So we're saying if this definition exists, if a function is differentiable, then it is definitely continuous. P implies Q, and the reverse is not true, okay? If the function is continuous, it doesn't mean that it's differentiable. So this is like P implies Q, direct implication. We good?
So in
So
which case it's differentiable? Sorry, Ustad, sorry.
in which case it is differentiable? Okay. There are functions that are differentiable and they are non-differentiable function. We will go through the examples. I'm just covering what does differentiability mean for now.
Okay,
So
okay.
you are differentiating a function and substituting values inside, checking the left-hand side limit and the right-hand side limit. Okay. So let's go over some examples. A function f is continuous at number a if, okay, so we did this definition for continuity, all right? I told you about the definition for continuity. So this is the definition for continuity. Limit as x approaches a of f of x is equal to f of a. Now, what are some of the continuous functions? Continuous function is like a constant function. F of x is equal to c. What does f of x equal to c look like? It's just a constant, right? Can be any constant. It's a horizontal line because the domain of that function is x is an element of real numbers. Okay. This is f of x is equal to c. Y is equal to c. Right? Doesn't have to be there. That value of c, if it was negative, it will be negative. Mx plus b is a linear function. So constant function is all continuous. There's no broken points. Linear function is all continuous. There's no broken points. Absolute value function is also continuous. Right? This is the absolute value function because what's a domain? As long as the domain is XER, X is an element of real numbers, it will always be continuous everywhere. What is the domain here? Yeah.
Positive and negative.
This is the absolute value functions. What is this? Exponential functions. All exponential functions are continuous. And all, most of the trig sine and cos functions are continuous. That's a cosine function. Okay. So we can look at general graph for each one. Linear function, let's look at the linear function. Linear function looks like this. Y equals mx plus b. Absolute value function, you know what it looks like. It's a V graph, right? There's no broken points here. E to the power x is an exponential function, right? So we have covered all this. E to the power x, that's absolute value x. And cos x starts from 1, right? And is waves. cosine wave, right? Right, so this is pi by 2, that's pi, 3 pi by 2, and that's 2 pi. And similarly, if you continue it on this side, it's going to carry on like that, right? This is negative pi by 2. That value is pi, negative 3 pi by 2, and you can continue forever, okay? That's a cos graph. Right, so these are all continuous functions. You can see there's no broken points in the graph. It continues forever. There's no broken points at all. Are we good? So let's look at discontinuous functions now. Discontinuous function. Check for the type of discontinuity. So this is what we need to focus on. Look at this. We've got f of x is equal to 0 and f of x is equal to 1. If you try to draw, sometimes it's good to draw the function and check what's happening. So I will just draw it and we'll be able to check for the type of discontinuity. F of x is equal to 0. 0 if x is less than 0. So is 0 if x is less than 0. So that point 0 is not, it's open circle. And that's my graph, okay? How do you draw y equals 0? There's a graph here, okay? So this is my one graph, see? And my second graph is y equals 1. So at 1 is t is including and it's y equals 1, okay? And this is y equals 0. So I want to know the type of discontinuity here. The type of discontinuity is clearly a jump. So we need to illustrate it. We need to show some calculation. Don't just draw a graph. So we're going to say limit as x approaches. We're doing left-hand side limit. So we investigating the type of discontinuity at x is equal to 0. So 0 from the left of f of x. What is 0 from the left? 0. Right-hand side limit is limit as x approaches 0 from the right. 0 from the right is greater than sign. I think I mixed this up. X is greater than or equal to 0. Yes. 0 from the left is 0. Yeah. No, it's right. And 0 from the right is greater than sign. So that's 1. We can clearly see that left-hand side limit is not equal to right-hand side limit. This implies limit as x approaches 0 of f of x does not exist. Does not exist. So we can say f is discontinuous at x is equal to 0, and the type of discontinuity, jump. Okay.
Sorry, we can find which kind of discontinuous from the graph, yeah? In that case, without calculating. But in the exam, for example, it will ask us to find which type of discontinuity is.
You need to show it.
Will be not enough.
The graph should be enough, but the graph gives you an indication of the graph kind of like gives you the answer. But sometimes the function is very complicated, so it's difficult to draw the graph. So you've got to test it out like this. Okay.
Oh, okay.
I can clearly see a jump. I can clearly see a jump between 0 and 1. See, 0 and 1, there's already a jump in the value. It's not the same. There's a jump in the value.
That's why I'm saying, yeah.
Yeah. So that's why you don't need the graph. You're supposed to show like algebraic calculations. The graph is sufficient to tell you the type of discontinuity. It's not enough for the proof. This is proving it. Okay. Let's look at the next type of discontinuity here. X squared minus 1 over x minus 1. So what I can do here is I can try to simplify this function. At x is equal to 1. So at x is equal to 1. Okay, let me try to simplify this function and check if I can get a graph. So this is x plus 1, x minus 1. And over x minus 1. Great. We can cancel out the x minus 1 and the x minus 1. So we are left with x plus 1. But x cannot be equal to 1. So we are checking for the type of discontinuity at 1. So how will I sketch a graph of y equals x plus 1? It's a linear function, but undefined at 1. Why is it undefined at 1? There's it here. Look at the original function. So x plus 1 is and the x-intercept is -1. And is undefined at 1. So it's a graph with the hole inside, okay? This is a value of 1, and this is the value of 2, because if I substitute 1 inside here, I get 2. So this is my linear function, and this is the graph of f of x, the original function. It's just that because I cancel the denominator out, you kind of cancel then a vertical asymptote out, right? So, but it's not a vertical asymptote, it's a removable point, okay? So how do we check this? We say limit as x approaches 1 of f of x that exists, that value is limit as x approaches 1 is 2.
Oh, 2, yes, sorry, 2.
As x approaches 1, the answer is 2. And f of 1, that does not exist, is undefined. So the limit does not exist. Can you see? So you can see this definition of continuity fails here. So we can say limit as x approaches 1 of f of x is clearly not equal to f of 1. So this is, if it was equal, then it will be continuous. So what we can say, f is discontinuous f is discontinuous at x is equal to 1, and the type of discontinuity is removable. Okay? Because the graph that has a hole there, removable discontinuity.
One question, sorry. Another. Here, when you simplify x squared minus 1 by x plus 1, x minus 1 divided by x minus 1, yeah? In that case, before simplifying, we should find domain, yeah? If I'm right.
Yes.
And then simplify, yeah?
Yes, that's correct. Remember, this x is equal to 1. This x is equal to 1 means you are testing the value. You're testing the continuity at x is equal to 1. That's what this 1 got nothing to do with the function. You're checking this 1 over here means it's a specified point. You must check for continuity at this point. Okay? The function itself is x squared minus 1 over x minus 1. You need to sketch that and check. Yes, so you are right. It's about the domain. So f is discontinuous at x is equal to 1. It's a removable discontinuity. Okay? Now, next one. We got f of x is equal to 1 over x. Now, you're checking for continuity at x is equal to 0. I think we've covered this already because this function, yeah, I covered this in the example, right? You can just go to example 3 and check. Yeah, I did cover this. I said f of x is equal to 1 over x at x is equal to 0. Continuity, there's it here, infinite discontinuity. This example is already covered here. Okay, so I'll leave that out. So we're just going to check here. Infinite discontinuity, right? The function is that, and that's a function. Wait, let me sketch the graph properly. Right, so limit as x approaches 0, 0, right? So we say left-hand side, limit as x approaches 0 of f of x is equal to 0 from the left is negative infinity. Is positive infinity, all right? And then you say limit as x approaches 0 of f of x does not exist. So we say f is discontinuous at x is equal to 0 and is infinite discontinuity, right? Right, so we did say, and you can say not only that, we can also, 1 second. We are saying this, we also need to say that f of 0 is undefined. So you can clearly see that the definition of continuity does not hold. The formula does not hold, like limit as x approaches 0 of f of x is clearly not equal to f of 0. So you have to say f is discontinuous, right? That's it. Let's look at the next one. Sine 1 over x. Okay. Sine 1 over x, I've sketched a graph for you here, right? This is a graph of sine 1 over x. So see what happens. Observing this graph,
It's not discontinuous, no? Because there is nothing missing in
yeah,
here.
it's discontinuous at 0 because it's like oscillatory. You are not getting any values. Look at this. So it's like oscillations. Because you see at 0 is undefined as well. See there. If I substitute 1 over 0, it becomes undefined, isn't?
Yeah.
So if you try the squeeze theorem here, remember sine x is between -1 and 1. Okay. Now, what was sine 1 over x? Is also between 1 and 1, because all I'm doing, I'm not changing the amplitude or nothing, I'm just changing the period. If you change the period, then the values will still remain between 1 and 1. Now, if I apply limit as x approaches 0, right? Nothing's happening. What's happening here is that this sine function is still remaining between -1 and 1. There's nothing to substitute here. Okay, so that's the reason why we say limit limit as x approaches 0 of f of x does not exist, right? And it doesn't exist because you see the sine function, sine or cosine function will be oscillatory. So f is discontinuous at x is equal to 0. Why is it discontinuous at x is equal to 0? Because if I directly substitute 0 here, you're going to get 1 over 0, which is undefined. F is discontinuous at x is equal to 0, and it is oscillatory. So in all functions, sine and cosine function will always be oscillatory, okay? It's because of the oscillations. See what's happening at 0. It's like jumping, -1 and 1, so you don't really know where it is, up or down. Are we good, guys?
Yeah, okay, I understand.
Right, excellent. So the main types of discontinuity you need to focus on is the first three. The fourth one sometimes, right, is a little bit more advanced technique because of the squeeze theorem and stuff. Okay. Now,
So oscillator is only in the sine and cosine, yeah? Only in the...
yeah, correct.
Okay.
Let's look at this type of, let's check this discontinuity. I just gave one more example to check what's happening. Let's observe the behavior of this function at x is equal to 2. So I've got two functions here. It's a split function, all right? X squared if x is not equal to 2. So how do I sketch that graph? X squared if x is not equal to 2. What is that? So let me sketch a graph of y equals x squared. It's a full function, all right? It's a full a quadratic function, but x is not equal to 2. So I'm going to make a gap here. So it's a graph for the whole, okay? It's everything but 2. It's a graph for the whole. Are we good?
Yeah, so
And
for the another one, just line, yeah?
no, just a dot.
Oh, for the second one. Oh, yeah,
Yeah.
just a dot?
5 and 2. 5 and 2 is just a coordinate. 2 and 5. 2 and 5 is just above this.
Oh, yeah, you're right, yeah.
Right. So you get a graph like this and that. So now we need to observe the behavior of this. So we're going to say limit. Let's check the limit as x approaches 0. Not 0, at 2. You're observing the behavior of the limit at 2. Okay, question. Remember, we need to check this definition. Limit as x approaches 2 of f of x. And I'm not putting equal to sign, and I need to check f of 2. So if I ask you what is f of 2, the value is 5. Okay. Now if I ask you what limit as x approaches 2, then you're going to look at not 2, left and right. So you go there, the value will be 4. Are we good? So we can clearly
So they're
see.
not
Can you go
equal.
over that again? It was kind of
What is
confusing.
that?
Can you go over that again? Like, why would it, if it's approaching left and right, it's 4, but if it's at 2, it's 5?
Because f of 2 is 5, is the value of the function at 2. What's the value of the function at 2? It is 5. There, if I put f of 2, you're going to 2 there. But when you go left and right, looking at the function, because approaching from the left, you're looking at this function. Approaching from the right, you're still looking at that function. If I ask you what's left and right, if I tell you to substitute 2 from the left, what value are you going to substitute? 1.999999. Where are you going to substitute 1.99999?
Left, negative.
No, I know it is left negative. Where are you going to substitute 1.999999? In the x squared function. It doesn't make sense to substitute into 5.
Oh, okay.
And 2 from the right.
I got it. Yeah, I got it.
2 from the right. Where are you going to substitute 2 from the right?
In the x squared.
Yes, you're still going to substitute into the x squared function. You can't go and substitute into the constant function because that is constant, is fixed value already. Okay, so that's why limit from left and right is same as saying limit as x approaches 2. You're just going to substitute 2 into x squared, right? Which is 4. So clearly this does not exist as well. So you're going to say limit. You can clearly see that these values are not equal. Okay. Can you see? They are not equal, correct? So we're going to say f is discontinuous at x is equal to 2, right? And what's the type of discontinuity?
Jumping. Oh, wait.
Why would we
For
say jump?
From 4 to 5, no?
We will say removable because the graph has a hole, okay?
Oh, yeah, removable, yeah, more better. Yeah, you're right, yeah. Because its graph is given up from there. Okay,
Yeah.
I understand, yeah.
So we say removable. Right, great. Now, let's look at determine the intervals for continuity. In other words, what are they asking you for? Intervals of continuity. They're asking you for the domain, okay? When is a graph continuous? What type of function is this? This
It's
is
a
a
cubic.
polynomial function. It's a polynomial function. It's not cubic, x to the power 5. Let's just call it a
Yeah,
polynomial
sorry,
function.
that's it.
Polynomial function, the domain is always x is an element of real numbers, all real numbers. Are we good?
So this is the answer?
Sorry.
This is the answer? The x
Yeah,
is an
that's the
11.
answer. Yeah. Intervals of continuity means what's the domain? That's another way of asking you for the domain. You can write the answer like this, or you can write it from negative infinity to infinity. Okay.
Okay.
Look at the next function. The next function we can simplify further. So we can say x cubed plus 2x over x plus 2, x minus 2. So when is it discontinuous? When it is equal to plus minus 2, correct? So the domain or the intervals for continuity, same thing. The domain
Any real
is,
numbers except -2 and +2?
yes, that is correct, but let's write it in interval notation. Let's go to -2 and 2. It can't be those values, but it can be everything else.
Yeah.
So we're going to write x is an element from negative infinity to -2, union -2 to 2, union 2 to infinity. Or you can write it as x is an element of real numbers except -2 plus minus 2. Okay. And if you're going to write it in the set builder notation with that curly brackets, you're going to say domain is equal to xer, comma, x is not equal to plus minus 2. Okay. So these are the different forms of writing, but remember to just try to use one method. Try to use the union method or interval notation. What about this one? So this is one entire function. First,
Can I answer this one,
everything.
mister?
Yes.
So x cannot be 3 and also cannot be -3.
It can be -3. Why it can't be -3?
Because 3 over here on this x squared.
X squared plus
It can
9
be
is all real
-3.
numbers. X squared plus
It
9,
can be
x can be
-3,
any
yeah.
real number. Yeah. It can be any real number. We're not
It's
dealing with complex
imaginary,
number.
no? It's imaginary in
No.
that case.
In AP calculus, we don't deal with imaginary numbers, only real numbers. Don't worry about imaginary numbers.
-3 squared still be 9? Oh, wait, never mind.
No, it does not work. So first, you went straight to the denominator. You're supposed to start with the square root function. Everything under the square root must be positive. So first, x minus 2 must be greater than or equal to 0. So x must be greater than or equal to 2. That's the first part. Then the second part is x cannot be 3 from this function. Now put everything together on the number line and then solve it. Easy. Okay, let's put everything together on the number line. So we got 2 there. So the answer can only be greater than or equal to 2. But it can't be 3. So there's a hole in the graph there. Okay. And that's the domain. How's that? So what's the intervals for continuity? What is the graph continuity? Intervals for continuity. What does intervals for continuity mean? The domain. So what's the domain?
X is greater than
Domain
2
is
and not equal
x
3.
is an element from 2, square bracket 2 to 3, union 3 to infinity. Make sense?
Yeah.
Yeah. It's
Yeah,
like
you can say that as well.
like
X
tricky,
is
yeah.
greater than or equal to 2, but x is not equal to. Yeah, and it's not tricky. You got to identify functions and solve them. I can change this into a log function. Right,
Yeah,
that's why you need to go over these linear functions and these types of functions that I've done with the logs and stuff, because it specifies the domains. See? Right, so let's go back here now, continuity. So that's it. There's no tricks here. You just got to know log functions. You need to know rational functions. Rational function denominator is undefined. Log function, everything after the log is always positive, greater than 0. And for square root function is always greater than equal to 0 if it's on top. But if the square root was in the denominator, you can't include 0. So it just x minus 2 is greater than 0. Okay? Okay, now we come to calculations involving continuity. Find the constants a and b that ensures that the given piecewise function is continuous for all real numbers. So you have this function here, you need to solve for a and b to make it continuous. Okay, so now let's look at the values where we're going to test for continuity. We're going to test for continuity at -1, and the next continuity we're going to test for is at 1. Okay? Yeah. So we're going to say limit, we're going to say at x is equal to -1, left-hand side limit must be equal to right-hand side limit. Why are we making them equal? Any idea?
because it's continuous, saying that it's continuous.
Good. So left-hand side limit must be equal to right-hand side limit. So we're going to say, this implies what is the left-hand side limit at -1? So we're going to say limit as x approaches -1 from the left, because we're approaching -1. Remember, -1 has left-hand side and right-hand side. -1 from the left is which function? It's the cubic function. And 1 from the right is x is greater than or equal to -1. That is the linear function. Okay, so now this is sorted out. Okay, let me just put this underneath here. Because there's 2 equations to work out. Now, if I try to simplify this equation, all I need to do is substitute -1 in the place of x and substitute 1 in the place of x. So we have an equation, 1 cubed, -1 cubed is -1. Sorry, we were substituting -1, right? So there's a negative here, right? So -1, so -a plus b. Are we good? So this is equation 1. Now let's look at equation 2 now. At x is equal to +1, what's happening? You got 1 and you got 1 from the left and 1 from the right. So you can say left-hand side limit must be equal to right-hand side limit. What's the left-hand side limit? Limit as x approaches 1 from the left. 1 from the left is where? X is less than 1. That's it here. 1 from the left, go to the green part. Is ax plus b.
Oh, but it also can't be x cubed, no?
It can't be x cubed because that is x is less than -1.
Oh, yeah.
We're checking we're checking the continuity of the limit at x equals to 1. There's 1 here, 1 from the left, 1 from the right. Those are the closest function, which is closest to 1. Right, so limit as x approaches 1 from the right. 1 from the right is where? Greater than or equal to 1 is x squared plus 2. Now substitute 1 inside x, because you chose your functions. Right, so if I substitute 1 inside x, I get a plus b is equal to? Yes?
3.
Yes,
3.
excellent. Yeah, and now I can solve for a and b because I got equation 1 and equation 2. So if I take this equation 1 and put it under equation 2, let's just move this equation there. is equal to -1. If I add them up, that's out. 2b is equal to 2. So b is equal to 1. We solve for b, right? Now to solve for a, if b is 1, you can just substitute into equation 2, right? B is 1, so
It's
a is 2. Good.
Yes.
That's it. Easy. So did we solve for a and b that makes the entire function continuous? Yes. A is 2, b is 1. This is problem solving using continuity.
So it will be discontinuities. We will make it not equal. Yeah. The right.
No, but
the
no.
right hand side.
Whenever you're solving problems like these, you're not looking for discontinuity. Discontinuous problems are the ones that I've done on top. Why is it discontinuous? Right. These are continuous problems. You're making the function continuous. When is this function discontinuous? Like C. It's discontinuous when the value is 3.
Oh yeah. Okay. Yeah. Okay.
Yeah, it's discontinuous when the value is plus minus 2. Over here, we're making the entire function continuous. So there must be no break in points in the graph. It must be like one piece of the function. So if the value of A is 2 and if the value of B is 1, then this entire function will become continuous. Great. Now let's look at differentiability. I just ran you quickly through differentiability. What's most important here is this important concept here is differentiable. If f is differentiable, what does it mean for a function to be differentiable? It means differentiability from the left must be equal to differentiability from the right. That's it. If the function is differentiable, then it is continuous. So if this definition of differentiability holds, then automatically limit as x approaches a of f of x must be equal to f of a. This must hold. It's a direct implication. The reverse is not true. Okay. So when is a function not differentiable? Right. So the functions are not differentiable when there is a jump, infinite, and removable discontinuities. You know what each of these discontinuities are. It's not differentiable at that point. When there's a sharp corner, what's a sharp corner? What's a cusp? Cusp is like absolute value of x. See the sharp corner here? Absolute value of x. Right? What is this? It's a sharp corner. This is what you call a cusp or the vertex. Vertex means it must meet at a V, right? So in other words, we call it a cusp. So it has a sharp corner, so it's not differentiable at 0. Right, so now I'm going to show this phenomena here. We're going to show this, right? I'm going to explain this, what that means. Remember, the absolute value of x is defined to be x if x is greater than or equal to 0, and negative x if x is less than 0. Right. Now, if I try to find the behavior of the limit at 0, so remember y is equal to f of x, which is, let's call it f of x, all right? So if I say f prime, the left-hand side derivative, f prime x from the left, where's the left-hand side derivative? We're checking at 0. Derivative from the left is the negative x, right? I'm getting -1. Are we good?
Just negative. Yeah.
And if I try a right-hand side limit, f prime, remember the x value is 0 here, okay? Now, because this is not a function, it already turned out to be a constant. There's nothing to substitute into. F prime x from the right, differentiating x, you're getting 1. You can clearly see that, yeah, you can clearly see the left-hand side is not equal to right-hand side. So f is not differentiable. Is not differentiable at x is equal to 0. Okay? It's not differentiable. Why? Because left-hand side is not equal to right-hand side for differentiability. Right, so now let's look at these functions here. So example 1, f of x is x squared plus 3x minus 5. This is differentiable, okay? It's differentiable everywhere because it's polynomial function. Okay? You'll find polynomial function left-hand side derivative must be equal to right-hand side derivative. It's differentiable everywhere at any point. What about if at x is equal to 0, it is not differentiable, okay? I just did that example now. Okay? F of x is equal to 1 over x, not differentiable at x is equal to 0. Why is it not differentiable at x is equal to 0? Because we have an asymptote there, right?
Undefined, yeah.
Remember when it is not differentiable? When there's discontinuities, jump, infinite, removable. Can we write this? Look here. I did write P implies Q. You can also write not P, not Q implies P. Not Q can imply not P. Right. This is called the contrapositive, I think. Yeah. Not Q implies not P. What does this mean now? Mathematically, it means if F is differentiable, that is P, then it is continuous. So what does it mean? If F is not continuous, then it is not differentiable. So that makes sense, okay?
It's not reversible, yeah?
Yeah. Just using a double negative. All right, so anyways, let's go back down. See, this function is not continuous, so it's not differentiable, okay? Look at this. 1 over x is not continuous at 0. We proved that. So it's not differentiable at x is equal to 0. What about this one here? This one is not differentiable at, is not continuous.
At 2?
Yes. Not continuous at x is equal to 2. So not differentiable. Not differentiable at x is equal to 2. Right. So great. You understand what differentiability means. Now let's solve some problems. Are the following functions differentiable at the points? So we're going to say left-hand side derivative. Remember, we are approaching at 1. Left-hand side is f prime x from the left. Right? So you can say at x is equal to 1, put a vertical line, substitution line. Right? And then let's find the derivative. We say ddx. ddx of what? From the left is what? X squared, right? When x is equal to 1. What's the derivative of x squared? 2x. Substitute x is equal to 1. You get 2. Are we good, guys? What does a vertical line mean? Just a substitution line. That's it. Are we good?
Yeah.
Yes, sir.
You will find it on the calculator. ddx of x squared at x is equal to 1. You can actually get that on the calculator. Show you now. Say ddx. Where's ddx? There's it here. Of x squared. Alpha x squared at x is equal to 1. There, the answer is 2. That's what it means. Now, what about right-hand side derivative? ddx, right-hand side means greater than 1. So 2x minus 1. Derivative of 2x minus 1 is just 2. There's nothing to substitute into, so that's my answer. So 2 is equal to 2. So we're going to say left-hand side is equal to right-hand side. Can anyone tell me if it's differentiable at 2 or not?
It's continuous, no? In that case,
No. We're checking for differentiability. Is it differentiable?
no.
It is. The left-hand side and right-hand side derivatives are the same at x is equal to 1. So
Oh
f
yeah,
is
yeah. Differentiable. Yeah, sorry. Yeah.
differentiable at x is equal to 1. If it is differentiable, then it is continuous. We don't need to write that down because they just asked for, is it differentiable? Let's check if this is differentiable at x is equal to 0. And is it differentiable at x is equal to 0? Let's check.
Well, the answer is just 0, right?
Okay.
But do we have to
We need to check it.
differentiate
We need to check it out. So say d g prime x. Let's try to find the derivative. So that's d dx of x to the power 1/3, right? Which is d dx of x to the power 1/3. So we can find the derivative of that. I don't know why I wrote d dx down again. That's 1/3 x to the power negative 2/3. Okay, which is 1/3 cube root of x squared. So now we already have x can't be 0. So g prime 0 does not exist, correct? Does g prime 0 exist? Does not exist, because if I substitute 0 into the derivative, it does not exist. So you can say not differentiable at x is equal to 0, right?
Yeah.
Yes.
Because if you substitute 0, you're going to get 0 in the denominator. G of x is not differentiable at x is equal to 0. What about this one? H of x is equal to x sine 1 over x. So now be careful, because this is x is not equal to 0 at x is equal to 0, right? So we're checking for differentiability. So we got 0. Let's check if it is continuous first, right? Check for continuity. Because remember, if it's not continuous, then it's not differentiable. Not, remember, P implies Q. Okay, let's say differentiability implies continuity, all right? Differentiability implies continuity, and not continuity implies not differentiability. Okay. So if you try to find limit as x approaches 0 of x sine 1 over x, by squeeze theorem, this answer will be 0, right? And we got f of 0, which is defined, which is 0. So which means it is continuous. That doesn't mean it's differentiable. Continuity does not mean differentiability. So we can say f is continuous at x is equal to 0, but that can't imply that it is also differentiable. So we got a problem, right? So what we can do here is we can say, let's check, we can differentiate the function, okay? Now to differentiate the function, we got to use something called the product rule here, x sine 1 over x. Because to differentiate 0, you just get 0. Let's try h prime x. Derivative of x is 1. Leave the sine 1 over x as it is. Plus derivative of sine 1 over x is cos 1 over x times the derivative of the inside which is negative 1 over x squared, and leave the x. Okay, so see what I've done? I differentiated that and I left the x. Does that make sense?
Yeah, make.
Now, I've got sine 1 over x plus, no plus, minus 1 over x cos 1 over x. Sine 1 over x minus 1 over x cos 1 over x.
Yeah, it's correct. It's correct, yeah.
Yeah, I know it's correct. I'm just checking how we're going to investigate the limits. So I want to substitute. Obviously, you're allowed to use a calculator. So h prime 0 from the left. So I need you to substitute 0 from the left inside this function and see what we're getting. What's 0 from the left? You're going to substitute a value which is very close to 0. So negative 0. Put 5 zeros and a 1. And over here, I'll put 0, 0, 0s, 5 zeros and a 1. And I need to know what's 0 from the right. I need to substitute into this function. Okay, so let's try this out. Sine, well, make sure your calculator is on radians, right? Now my calculator is on radians mode, shift mode radians. Sine 1 over 0 negative 0.0001. Subtract 1 over negative 0.0001 cos 1 over negative 0.0001. 4 zeros and a 1, okay? I'm getting an answer which is negative 999. Are we getting negative infinity there? Yeah. Kind of, because if I put more zeros here now, what's happening? Put 2 more zeros. Is it getting bigger? Did you try it out?
No,
And I think
just think it's getting bigger.
Okay, over here, I think we're getting positive infinity. Okay? Are we good? So I think that's what's happening, negative and positive. So there's an infinite discontinuity, all right? So we're going to say left-hand side is not equal to right-hand side. Guys, you need to check this out. Just substitute those values and check and keep on changing the values too. So we can say f is not differentiable at x is equal to 0. Are we good? Next one.
Yes, so
We got absolute value of, yes. Sorry.
I was just asking, is this the last question?
No, we have 2 more after this. I won't be long. Yeah, after this is just one more question about A and B. So that is differentiable everywhere. So let's see. We got x minus 2 plus x at x is equal to 2. So we need to split up this absolute value function. Is x minus 2 if x minus 2 is greater than equal to x, and negative into x minus 2 if x minus 2 is less than x, and we still need to add a x there, right? So it's x minus 2, sorry, not x, 0. If x is greater than equal to 2, and negative x plus 2 if x is less than 2. You still need to add a x. Now when you add a x, you need to add the x to both pieces, okay? So that's going to become 2x minus 2. If you add the x there, it's going to become 2. Okay? Because you split this function up. If you're going to add a x, you're going to add to this function and to that function, right? So now we're going to check derivatives. at 2. All right, so we're looking for less than sign, less than equal to sign here, greater than and greater than equal to sign here. So left-hand side, ddx, left-hand side will be derivative of the function from the left-hand side function at 2, right? Which is derivative from the left at 2, which is just 0. The right-hand side function, f prime positive. We can say put a vertical line, say x is equal to 2, right? Derivative from the right, which is positive. It's checking the right-hand side derivative. You just get 2. So clearly you can say left-hand side is not equal to right-hand side. So f is not differentiable. Okay. F is not differentiable at x is equal to 2. Now last example with a and b. Find the constants a and b such that piecewise function is differentiable everywhere. So what does differentiability means?
It can be
F
derived.
prime.
Left-hand side equals to the right-hand side.
Yeah, f prime x at x is equal to 2 must be equal to f prime x at x is equal to 2. So from the left-hand side, we can say ddx, derivative of what? Left-hand side, x squared plus ax plus b. And what's the function here?
4x minus 2.
From 4x minus 2
Yes. So derivative of the
at
first
x
one
is
will
equal to
be
2. So this one of
2x.
2x
It will be plus a.
plus a at
Just 0.
x is equal
Plus like this, yeah. And
yeah.
it will be 4.
No need to substitute that there, all right? Because
Yes.
that's not a function. If you substitute 2 inside here, you get 4 plus a is equal to 4. If you substitute 2 inside this derivative function, 4 plus a is equal to 4, so a is equal to 0. Great. We got the value of a. Now the problem is the value of b. Okay?
B is constant, no, in that case.
B is constant, but what constant value is it? Got a
It
problem.
can be from negative infinity to positive infinity, no? In that case.
It can't. Now this is where the theorem comes in. What did I tell you? If the function is differentiable, then it is continuous. So there's the differentiability. What does continuity mean? Limit from left must be equal to limit from right. Limit from 2 from the left must be limit 2 from the right of f of x. So let's substitute 2 from the left. What is 2 from the left? The left-hand side function. Substitute 2 inside here. What do you get? If you substitute 2 inside the left-hand side function, you get 4 plus 2a plus b. Are we good?
A is 0 actually, no? We can just put it. It will be just 4 plus b.
Yeah. A is 0, correct. But I don't want to do that now. Let's substitute the entire function. Let's substitute 2 in the right-hand side function. Substitute 2 here. You get 8 minus 2. Right, now we can say a is 0, which we saw from differentiability. So that is 0. So you got 4 plus b is equal to 6. So b is now equals to 2. Right, and this brings us to the end of our differentiability and continuity session. I hope you understood everything. Just gonna all right, guys. Any questions?
Yeah.